Good morning. Class 4 of Unit 4, Solid State Control of Synchronous Motor Drive. So till last class, we discussed control techniques for synchronous motor drive. I mean self-control and separate control based VSA and CSA fed synchronous motor drive. We discussed in the last class. The next one, cycloconverter fed synchronous motor drive. So we know the basic operation of cycloconverter, which is converts fixed AC voltage into variable AC voltage and variable frequency. So for converting fixed AC voltage into variable AC voltage, we are implementing three-phase cycloconverter. So with the help of 18 thyristors. So these 18 thyristors are connected with the help of these 6 reactors. So these reactors used for making as current as a circulating current. So here, so each phase contains two back-to-back three-phase half converters. I mean, so while operating under positive half cycle, so these three thyristors are used under A phase. So similarly for negative half cycle operation, these three thyristors are used. So similarly, so each phase has 6 thyristors. 3 are connected for positive half cycle operation, 3 are connected for negative half cycle operation. So, so these three-phase cycloconverter is operated under two mode of operation: circulating current mode and non-circulating current mode. So under circulating current mode, so in each phase, both half converters, I mean positive half converters and negative half converters, both are operating. Then what will happen? It will make a circulating current with the help of reactor. So that's called circulating current mode of operation. So that time the output A phase is generated, variable AC voltage is generated. So similarly, it can be done for both B phase and C phase. Whenever both half converters, positive half converter and negative half converter, both are operating, then current flow will take place between these two. Then with the help of reactor, so then the variable AC voltage is generated as output voltage. If it is non-circulating current mode, either positive half converter or negative half converter, either one is on. So with the help of that, the variable AC voltage is generated. So during non-circulating current mode of operation, so no need of these reactors. So with the help of these two modes, circulating current mode and non-circulating current mode, we are operating the three-phase cycloconverter. So now for controlling these AC thyristors, we are using closed loop operation for switching pulse generation. So now from the output of rotor, we are measuring the speed signal, and from the stator side, we are measuring the current signal, actual current signal. So with the help of the speed and current signal, we're going to generate the firing pulses for these 18 thyristors. Now the actual speed is measured, which is compared with the set speed value. We are getting the error speed value here. With the help of PI controller, it's converted into voltage parameter. Similarly, so the current signal is measured in the stator side, so which is compared with the reference current signal. So the error current signal is getting here. So it's converted into voltage signal with the help of PI controller. Now by comparing these two voltage values with the help of firing circuit, you are generating the firing pulses for the three phase RYB. So with the help of that firing pulses, we are controlling the 18 tie resistor placed in the three-phase cycloconverter fed synchronous motor drive. Next one, synchronous motor for power factor control. So this is synchronous motor is placed here. See the block diagram. Here the synchronous motor is placed here. So we have to give a two supply. One is for stator. So for stator AC voltage, with the help of DC supply, giving to inverter cycle, the DC is converted into AC. That AC is directly applied to stator of synchronous motor drive. Then for controlling the rotor, we need a separate DC excitation. So it's generated with the help of rectifier from the AC supply. So AC is converted into DC with the help of field rectifier. So that DC is connected to rotor. So it's used for DC excitation of the rotor. So now we're going to do the power factor control. So for in the stator output, you are measuring the power factor, actual power factor value with the help of power factor calculator. So that's compared with the desired power factor value. So by comparing actual power factor and desired power factor, you are getting the error value in terms of power factor. So we have to generate a firing pulses for this rectifier circuit. So for that, we are converting this power factor value into voltage value with the help of this PI controller. So here it's converting power factor parameter into voltage parameter. So with the help of phase control and firing circuit, we are generating the firing pulses for the field rectifier. So with the help of these, so the power factor of the synchronous motor is controlled. So it's the closed loop operation is operating until the synchronous motor reaches the desired power factor value. Next one, closed loop control of synchronous motor drive. So otherwise we can call load commutated fed inverter synchronous motor drive. See the block diagram. So first see in terms of open loop operation. So the AC supply is applied to source side converter. So source side converter is nothing but is a rectifier. It's going to convert AC voltage into DC voltage. To remove the ripples present in the DC, we are using L filter here. So after removing the ripples, it's connected with the load side converter. Load side converter is nothing but is an inverter. It's acting as an inverter. So this DC voltage is converted into AC with the help of load side converter. It's connected with the synchronous motor drive. So it's operating under open loop connection now. So for generating the switching pulses for the source side converter and load side converter, we are making a closed loop operation. So here the two parameters are taken for this closed loop operation. One is current parameter, other one is a speed parameter. So with the help of terminal voltage sensor, we are measuring the speed value and frequency value here. So the speed is taken as a actual speed, which is compared with the reference speed value. So by comparing actual and reference speed value, you are getting the speed value in terms of error. So with the help of the speed controller, we are converting speed parameter into current parameter. Actually, the speed controller is acting as a PI controller. So with the help of the speed parameter is converted into current parameter. For limiting the current value, we are using the current limiter. So this current is called as a reference current. After the current limiter, we are getting the reference current value. Then actual current is measured from the system. So by comparing this actual and reference current value, we are getting error current value. So obviously we have to generate the firing pulses for the source side converter, I mean rectifier. So for that, we are converting this current parameter into voltage parameter with the help of this current controller, and firing circuit also placed. With the help of that firing circuit, we are comparing the two signals. Then based on that, the switching pulses are generated for this source side converter. So now the switching pulses are generated for the source side converter, I mean rectifier, with the help of speed and current signal. So coming to the source load side converter, so here with the help of frequency and voltage, we are generating the switching pulses for load side converter. So from here, we are getting a frequency value. I mean, we know the error speed value. From that error speed, we are converting into frequency value. We already know ns should be equal to 120 f divided by t. With the help of that relation, we are getting frequency value from the speed. So with the help of sine omega m, we are converting into variable frequency value. So already we measure the actual frequency from the system. With the help of phase delay, we are comparing the two frequency values. We are getting error frequency. With the help of that frequency, the switching pulses are generated from the firing circuit for the inverter circuit. For the load side converter, we are generating the firing pulses based upon the frequency value. For source side converter, we generated the frequency value based upon the current and speed. So this is a closed loop operation of synchronous motor drive. Otherwise, we can say load commutated fed inverter fed synchronous motor drive. This is the explanation for the previous block diagram. The last one, ether source inverter. So the basic function of ether source inverter to boost the inverter output voltage. It provides better performance compared to conventional DC to DC boost converter. So the generally ether source inverter is a mixer of two inductors and two capacitors connected in XA. So it's used to boost the inverter output voltage with the help of these inductor and capacitor design. Based upon the size and design of this inductor and capacitor, the output booster level can be decided. So here the ether source inverter is operating under two mode of operation. One is shoot through mode, another one is non-shoot through mode. So also the ether source converter used to reduce the ripple current in the particular circuit. So this one is edge source inverter fed synchronous motor drive. So this edge source inverter is placed between DC supply, input DC supply and inverter. So three-phase VSI inverter. So the output of three-phase VSI inverter is connected with synchronous motor drive. So now based upon the control of edge source network, we can boost the inverter output voltage. By boosting the inverter output voltage, we can provide a better input voltage to the synchronous motor drive. We can provide a better control to the synchronous motor drive. So now the two inductors and two capacitors are connected in XA. So this network is called edge source network, and one more diode is placed here. So when the shoot through mode is operating, this diode will become as a reverse bias. When the inverter is operating in a non-shoot through mode, then this diode will be in forward bias condition. So coming to the modes of operation of inverter, so we already know this edge source inverter is placed between the DC supply and inverter circuit. So this is the normal basic edge source network for two-level inverter circuit. So here the first diagram I mean the B1 which explains shoot through mode of operation. Shoot through means nothing but in a particular leg or phase. I mean A phase or B phase or C phase, any phase in a particular phase. Both switches, I mean all the switches are in on condition. Then what will happen? The short circuit will be takes place. Then it's become as short circuit. I mean it's become as a zero output voltage. So during that time, the inductor and capacitors are charging. So that's called shoot through mode of operation. During non-shoot through mode of operation, so what will happen? So same like a normal inverter operation, either one of the switch, I mean either the S1 switch or S2 switch in the A phase is getting on. So that time the inverter is operating as a normal VSI inverter. So during shoot through mode of operation, this capacitor inductors are charging. So during the next cycle, what will happen? I mean during normal mode of operation, this applied DC voltage plus the amount of voltage charged in the capacitor both are adding. So what will happen? The output voltage becomes twice or thrice that of applied input voltage. That depends upon what about the size and capacity of the invert capacitor and inductor. So based upon then the output voltage of the inverter is boosted. Once the output of the inverter is boosted, it's connected with the synchronous motor drive. Then we can remove the amount of ripple current present in that. So based upon that, the performance of the synchronous motor is improved. So it's called as edge source inverter fed synchronous motor drive operation. So we are coming to the end of unit 4. So that's all about the syllabus in unit 4. Thank you.